Hello, welcome to your first tutorial on organic chemistry. This one's going to be on chemical formulae. So we're going to look at different types of chemical formula. I've split this tutorial into two parts, which I'll explain in a second, so that you can possibly have a little break in between if you want to. And that's just because this year you've got double lessons, so where usually you'd have 2 lessons in a week and you'd do tutorial lesson, now we have twice as much to do in the week, so that you've got a double lesson at the end of it on a Friday. So here are your different types of chemical formula that we're going to go through. 6 different types that I want you to learn about at A level. So we've got molecular formula, which you should be familiar with. Structural formula, I'd hope you have some idea of structural formula as well. And displayed formula, you will have seen quite a few of those in GCSE. Then we get on to some that you might not have seen before. So we've got empirical formula, general formula, and skeletal formula. We're going to work through these. So I've split the different formula into 2 different mini tutorials. So first of all, we're going to look at these 3, the simplest ones: molecular, structural, and displayed. Now, it's important to know that in your A level, you will be expected to interpret molecular, structural, displayed, empirical, general, and skeletal formula. You'll also be expected to be able to write them yourself or draw them yourself, and you may be asked to define molecular formula, structural formula, and give a definition for them, and it is important that you learn those definitions pretty early on. So let's have a look at the first one. Okay, so first up we've got molecular formula. Now, this is something that you should be very familiar with from Key Stage 3. So in the past, when you've been asked to write a chemical formula for something, you've written the molecular formula more likely than not. So H2O, water, CO2, carbon dioxide, these are molecular formula. And the molecular formula shows the actual number of atoms of each element in a molecule. Now, just to remind you, as you're watching these tutorials, you should have a notebook open in front of you, and you should be making notes as you would in a normal A-level lesson. This is so that when you do get back into lessons, you don't have to waste time just making notes. You can use all of that lesson time with all the support you've got around you to apply your understanding of what you've seen in this tutorial and in the next part of the Formula 1. So make sure that you are making notes, bring them to class, let's see what you've got, and then we can start practicing using this information. Okay, so let's have a little look at some examples of writing molecular formula. So we've got some compounds here. It says how many elements we've got and how many atoms of each element we've got. So in the first one, we've got 2 carbon atoms, we've got 6 hydrogen atoms, we've got 1 oxygen atom. So to write the molecular formula for that compound, you put your carbons first. So the number of carbons we've got is 2, so we put 2 as a subscript, so that's small and at the bottom. Next we write hydrogens, so generally it goes carbons, then hydrogens, then everything else comes after that. So the hydrogens, capital H, and we've got 6 of them, so subscript, small and at the bottom. And we've got 1 oxygen atom. So 1 atom, you don't need to write a subscript number, just needs to appear. So there's the 1 oxygen atom. So C2H6O consists of 2 carbon atoms, 6 hydrogen atoms, and 1 oxygen. Okay, so the next one, we've got 1 carbon and 4 hydrogens, so that's methane. So carbon comes on its own, only 1 of them. Hydrogen, there are 4 of them, subscript at the bottom. This should be a recap, it should be something that you're very confident with. Okay, just to confuse you, we've written them the wrong way around. We've got the hydrogens first and then the carbons, but we do have carbons, we've got 2 of them, we've got hydrogens, and we've got 6 of them. Please make sure that your subscript numbers are small and are at the bottom, because if there's any dispute over that, you might not get a mark, and you need to make sure that you're getting these simple marks. Okay, finally, we've got 3 chlorines, 6 carbons, and 11 hydrogens. So we'll put carbons first, and we've got 6 of them. Then hydrogens, we have 11 of them, and chlorines, we have 3 of them. So that is it for writing molecular formula. Now, remember, you need the ability to interpret these formula, you need the ability to write these formula, but you also need to remember the definition. So the molecular formula shows the actual number of atoms of each element present in a molecule. Learn it, make sure that you know it so that that question is easy marks. Okay, so whiz through that one because that should be fairly straightforward. So moving on then to the next type of formula. This is called displayed formula, and it's kind of what it sounds like really. The formula is displayed for you to see what is where, the arrangement, all the bonds, everything, so that you know what that compound looks like. So I'm going to show you through an example. So we've got some atoms present in a compound here. We've got 2 carbons, 6 hydrogens and 1 oxygen. I'll show you how to draw that in displayed formula. But first you need to know that a displayed formula shows all atoms, the arrangement of atoms, and the bonds between them. In a molecule. Okay, so it shows you pretty much everything. It's very useful formula. It does give you a lot of information. So, looking at these atoms that we've got then, we have got 2 carbon atoms. So organic chemistry is the chemistry of carbon, because carbon can bond to itself over and over and over again in loads of different formations. So you get long chains, you get loops, you get branches, and that's why organic chemistry is such a big branch of chemistry. So when you're drawing out your displayed formula, start with a carbon skeleton, a carbon backbone. So we've got 2 carbons, so we'll draw them in. That's our carbon backbone. Generally, in organic chemistry, hydrogens sit all around the outside of your carbons. Now, I'll put one there, and I've got to show the bonds because it's a displayed formula. One there and one there. That takes us to 5 hydrogens, but we've still got to put this oxygen in as well. So if we put the oxygen in and then the hydrogen, that finishes off one example of a displayed formula with those atoms in. Now, if you're looking at that displayed formula and thinking, well, how do I know that that oxygen goes there and then the hydrogen goes on the end? There are some rules to help you with that. So very quickly, I'll run through some little tips. So first of all, carbon atoms tend to make 4 bonds, nearly always. You will see them with 4 bonds. So if we pick a carbon atom here, let's go with this one. We've got 1 bond to hydrogen, 1 bond to carbon, 1 bond to hydrogen, 1 bond to oxygen. It makes 4 bonds. That's a stable arrangement for a carbon atom. Hydrogen atoms, you can see from my displayed formula, 1 bond. Okay, so that's why they usually go around the outside. So just making 1 bond into a carbon atom, or in this case, into an oxygen atom. Oxygen, take a guess. Look at my diagram. 2 bonds. That can be single bond, so we've got a single bond here and a single bond there, or it can double bond, and carbons can double bond, and we'll have a little look at that as we come across different compounds. But you can see that my displayed formula shows all of the atoms present in the compound, it shows the arrangement of them, and it shows the bonds between them, and I haven't missed out any of the bonds. That's really important. So as you're doing a bit of reading around and you're having a look at different things, you might find somebody has put, here is the displayed formula of, and they've missed some bonds out. Personally, I wouldn't risk that in an exam situation. So some people will stick CH3 together with a bond there and the rest of the molecule. Just draw them out. So I would take that off, those 3 hydrogens, and stick them exactly where they should go. 1 there, 1 there, and 1 there, and the rest of the molecule that way. Okay, so that is displayed formula. Now, there are obviously other ways, some people might have noticed, of arranging these atoms with different arrangements of bonds where you're still meeting these rules, where carbon's got 4 bonds, hydrogens have got 1, oxygens have got 2, but the molecule looks different, and we will come to those later as well. So don't worry if you've noticed that that's not the only arrangement that you could draw that in. We'll deal with that later. Okay, and on to structural formula. So people get a little bit confused between displayed formula and structural formula because both of them give you structural information about how the molecule is arranged. But your structural formula, you just need to remember, it looks a little bit like molecular formula, so it's a line of text rather than a diagram. Displayed formula looks a little bit more like a diagram. So I've got some displayed formula here. So these are my 3 compounds drawn out in displayed formula. We can work out the molecular formula for these. So this is the simple one. So in the first one, we have got 1, 2, 3, 4 carbon atoms. So C and a subscript 4. And we've got 8 hydrogens, 9 hydrogens, 10 hydrogens. So H with a subscript 10. Nice and easy molecular formula. And we can do that for the other 2 as well. So there we go. Middle one, C3H6O, and the bottom one is C6H12. Now, looking at the molecular formula, it doesn't give you information, structural information. So like I was saying in the previous slide, that is the molecular formula for this compound, but actually if you had that molecular formula and you had to draw a displayed formula from it, you might draw that, but you might draw something different. Same with this one. You might draw it in that arrangement, you might draw something different. So a structural formula is the step up from molecular formula, and it does give you information about the arrangement of the atoms. So not just how many there are, but where they are and what they're joined to. So to write a structural formula, all you have to do is take each carbon atom in turn and discuss what it's connected to. So I'm just grouping carbon atoms with what it's connected to here. So in the first one, we've got a carbon atom, and it's attached to 3 hydrogen atoms, so H3. So that's that carbon atom there, and it's 3, and then it goes on to the next carbon atom, so you're ready to write the next carbon in. So then we've got a CH2, so that's a carbon with 2 hydrogens attached. We've got another CH2, running out of space a little bit, and then we've got a CH3. So that is the structural formula for that compound. There you go, a little bit neater. So it does give you more information than just C4H10. If you count up the atoms that are in that structural formula there, you will get, you've got 3 hydrogens, 2 hydrogens, 2 hydrogens and 3 hydrogens. There's your 10 hydrogens, and you've got your 4 carbons. So it's the same formula, it just breaks it down and tells you exactly how it's arranged. So you know by looking at this, it's a straight chain molecule and it hasn't got branched carbons coming off elsewhere, because the structural formula tells you that. So looking at the second one then, we take the first carbon and find out what that's attached to. So it's again attached to 3 hydrogens. So we've got a CH3 part of the molecule. The next carbon is attached to 2 hydrogens. So we've got a CH2. And the final part, the carbon, is there, and it's attached to a hydrogen and an oxygen. So a hydrogen, just the one, and an oxygen, just the one. That gives you structural formula. Now, as we go on a little bit later in coming weeks, you will learn about functional groups. That's families of compounds that all have similar properties. And what you'll be able to do is you'll be able to look at structural formula and see that that part is equal to that part, and you'll know about which functional groups are present by looking at the structural formula. So that's something that will come with practice. But structural formula is obviously very helpful because it does give you a little bit more information. It's a little bit easier to write out than a displayed formula where you've got to draw it and make space for everything. But it's better than a molecular formula. So quickly before we move on, structural formula shows all atoms carbon by carbon, including hydrogens and functional groups, which is that, like the CHO. Functional groups. So that shows you the reactivity of the compound. It shows you how certain atoms are arranged to give certain chemical properties. Right, finally, last one down at the bottom. We have got, first of all, this alkene part of the compound. So we've got carbons that are double bonded. Now, that double bond can be shown in structural formula. So I'm going to draw it in. In fact, I'm going to move it over slightly. Otherwise I'll run out of space. So there's my carbon-carbon double bond. You're okay to draw in a double bond in structural formula because it's important, it's there, and you need to know it's there, but the other bonds don't really matter. Now, to the left of this, you've got these 2 hydrogens. So I'm going to put that at the start. So 2 hydrogens attached to a carbon, which is double bonded to another carbon. That gets us to here. That carbon's got hydrogen coming off it, so I'll put the H in as well. Now that's that bit out of the way. That's just a little bit confusing because you might think you'd put CH2 for a carbon with 2 hydrogens coming off it. But if you were to write CH2 and then put your double bond in, it shows that your double bond's coming from hydrogens when it isn't. It's coming from the carbon. So we tend to draw it the other way around. Okay, so now we are, where are we? Here, we've drawn that hydrogen in. Now we're here, CH2, nice and easy. Then we get to this carbon, which has a hydrogen coming off it, a CH3 coming off it, and a CH3 coming off it. Now you might consider this one to be the next part of the molecule. So we've got this carbon, the central carbon, write that in. It's got a hydrogen coming off it, so we write that in. And it's got a CH3 and a CH3, so you can class them as 2 CH3 groups. So in brackets, you've got a CH3, close the brackets, you've actually got that twice. So it's a little bit of a more complicated one because obviously you've got the double bond, which makes you have to write things back to front at the beginning, and then you've got things coming off, so you've got branches. So generally the rule is if you've got something coming off, an extra branch, you can put it in brackets to say that's coming off. If you've got 2 of the same, you could put them both in brackets and say you've got 2 of them, as long as they're in the right part of the molecule. Okay, so that is structural formula. Better than molecular formula, probably not quite as good as displayed formula, but gives you an awful lot of information about the compound. So if you need to have a little look at that, make sure you kind of grasp that and get that in your head so that we can practice it in lesson. Okay, so that concludes the first part of the formula. So we've got molecular formula, displayed formula, and structural formula. You might want to take a little break now before moving on. So we do have a second part that you need to do before you go to the lesson, but if you want to take a break, maybe do this on another day, that's fine, as long as it's done before the lesson. Okay, so pause here if you're having a little break, and if not, we'll move on. Okay, so part 2, introduction to organic chemistry, formulae. So a little bit more complicated, which is why I've got this lovely diagram here to frighten everyone. How you can draw things like that, that's another type of formula that we're going to look at now. Now we're going to look at something. So we've got our 6 types of formula. We have done molecular, structural and displayed, and we're now going to have a look at skeletal, general and empirical formula. Okay, so first of all we have got empirical formula, and I'm going to give you the definition of empirical formula. So this is the simplest whole number ratio of atoms of each element in a molecule. Okay, so it's simplifying it down. So if you've got kind of 10 hydrogens to every 2 carbons, you could simplify that. You could divide both of those numbers by 2, so you could get it down to 5 hydrogens for every 1 carbon, and that's essentially all an empirical formula is. So again, we're going to start with molecular formula. We've got the displayed formula already given for these 3 compounds. I'll put in the molecular formula, which should be dead easy by now, and then we'll look at how we can simplify that down to an empirical formula. Okay, so there's your molecular formula, same 3 compounds that we just had for the previous examples. So empirical formula, we're just simplifying. So can you divide these numbers by the same number to simplify it down? So what goes into 4 and also goes into 10, how simple can you get it? So first of all, you can definitely half it. It's both these are even numbers, so that's an easy place to start if you're not good with ratios. So if we half it, we've now got 2 carbons and we've got 5 hydrogens. Is there anything else that you could divide both of these numbers by? No, there isn't. So C2H5 is the empirical formula for butane, which is C4H10. So it's the simplified version, simplest ratio, whole number ratio of atoms in each element. Okay, moving on to the second one. We've got 3 carbons, 6 hydrogens and 1 oxygen. So what number can you divide 3, 6 and 1 by? You can only divide them by 1. So if you divide each of those numbers by 1, because you've got this oxygen on its own, this is telling you you're not going to get it any simpler because you can't get it any smaller than 1. So your empirical formula, 3 divided by 1 is 3, 6 divided by 1 is 6, 1 divided by 1 is 1. In this case, your empirical formula is the simplest ratio. So don't be afraid if you're looking for an empirical formula and actually you can't simplify it. Maybe the molecular formula is the same as the empirical formula, which is the case quite often. Okay, and finally, nice and quick, we've got C6H12. What can you divide both of those numbers by to get down to the simplest ratio? Straight away you could divide them by 6. So, carbons, 6 divided by 6 is 1, so I don't need to write that in. Hydrogens, 12 divided by 6 is 2. So that one simplifies down massively. So we start with C6H12. Your empirical formula for that compound is CH2. For every 1 carbon atom, there are 2 hydrogen atoms available. And that was very quick, but that is empirical formula. There are other things that you can do, analysis, percentage by mass, that lead you to empirical formula, but we'll bother with that later. For now, we're just looking at what each formula is, the definition of it, what it means, can you write them yourself, and can you interpret them? So we can move on. Okay, next we've got general formula. General formula is a bit of a weird one. General formula is kind of an algebra expression. It's a way of showing the pattern that families of chemicals have in their formula. So if you get a family of chemicals that are all very similar, they're in the same homologous series or the same family, they will have the same functional groups, and generally they will differ by a carbon and 2 hydrogens. So if I just show you an alcohol, displayed formula, that's one alcohol. There's another alcohol. And you can see that really the difference between them is just the chain length gets longer by one lot of CH2. So you're shoving that in the middle. So you could do it again. These are a family of chemicals. And because they only differ by CH2 each time, they're just getting a little bit longer. They've still got the same functional group, so the same important part of the molecule that gives it its reactivity. You can write an algebraic expression to show what the formula of that would be. And we do it by saying, for a certain number of carbons, how many hydrogens and other things do we have? So for a certain number of carbons, we write that as Cn, for a number of carbons, and then you can write the rest. So if you look at each of these alcohols, let me just get rid of some of these lines. Okay, that's better. So if you look at each of these, you can say that for any number of carbon atoms, you can work out how many hydrogens and things it would have. Now we know they've all got an OH group on the end, so we know it's going to end with an OH. But in terms of algebra, how do we work out how many hydrogens are here, here, and here? Because that's the bit that we're missing in the middle. How many hydrogens? Remembering that we still got that one from the alcohol over this end. So, basically, if you look at each of these compounds, you've got a string of carbons there, and above and below you've got hydrogen on each of them. So you can double it, and then you've always got one on the end. So if you take however many carbons you've got, double that number so that you get these hydrogens, and add 1, you will get the right number of hydrogens for that compound. So take this number of carbons, double it, gives you those hydrogens, and add 1 gives you that. This number of carbons, double it to get you those, and add 1 gives you that one. So for your H's, you take N, you double it, and you add 1. And that is your general formula for alcohols. So it does look a little bit odd having this OH group separate over here, taking this hydrogen away from these hydrogens, but generally that's what we do with functional groups. So when you've got a part of a molecule, it's very important for how that molecule behaves. We can take it and separate it, so that OH is very important as a functional group, so we can keep it separate in the formula. Okay, so looking at that general formula for alcohols, then you can now use this to figure out how many hydrogens and things you would have, what the actual formula would be for a bigger chain. So if you had a molecule that had 8 carbons in it and it was an alcohol, you change Cn to C8, which we know it's got 8 carbons, and then you just use the algebra up here to work out what else it's got. So H, 2N, so double N, double 8 gives you 16, plus 1 that's going to take it to 17. OH, so let's write that out again, C8H, that's now 17, OH. And I'm not going to waste your time doing it, but if you were to draw that out with 8 carbons and all the hydrogens and an OH group sticking out, that's how many you would have. So your general formula is quite good for predicting how many hydrogens and other elements you would have based on a certain number of carbons. So you will come across other general formula, ones for alkanes and alkenes and things like that. And generally, as we come across those functional groups and we learn about them in detail, then I will bring in the general formula. So as long as you kind of know what it is, algebraic expression to show how many different types of elements you'll have within a family of chemicals, then that's fine for now. And we'll pick that back up later on. Okay, onto the lovely one, skeletal formula, the one that looks really smart. So this is an example of skeletal formula, and you'll see that it's got lots of hexagons and lots of lines in it. And this is the sort of stuff you'll see kind of on TV shows and films when they try and show something really clever is being made, medicines and things like that. Okay, but as with everything, there are rules. So if you learn the rules, you can learn how to draw things in this format. So what happens with skeletal formula is you remove all of the carbons and all of the hydrogens, and you just draw the bonds between the carbon atoms. So I'm going to show you the top one here. Okay, so this is that compound there. It's just drawn displayed formula or skeletal formula. Now you should be able to see straight away the benefits of drawing in skeletal. It's just so much quicker, so much easier. If you've got to draw something very complicated like a drug that you're trying to synthesize in a lab, you're going to want to draw it in skeletal formula because it'll take you forever drawing out bonds and hydrogen atoms. So it's worthwhile. It just looks a little bit odd at first. So what you need to understand is every line that's drawn that meets another line, every line is a bond between carbon atoms. So if I change the colour of my pen and show you this, we've got this bond here, carbon to carbon, is this one here. Then we've got carbon to carbon is that bond there. Carbon to carbon is that bond there. And there are no other bonds in that compound that go between carbon atoms, so you don't have to draw any other lines in. Hydrogens are omitted completely. So you don't draw the hydrogens in, and additionally, you don't draw their bonds in. So if you've just got hydrogen sticking off of a carbon atom, don't draw it in. If you've got hydrogen that's part of a functional group, then you will want to draw it in. We'll come to that in a little bit. But for simple alkanes, this is all you need, just these zigzag lines. So each line, remember, is a bond between carbon atoms. Now, this is where people get stuck. So if I show you pentane, pentane means 5 carbons. So you have got carbon 1, bonded to carbon 2, bonded to carbon 3, bonded to carbon 4, bonded to carbon 5. Now this is what people do that gets them a little bit confused. If I ask you to draw a pentane with 5 carbons in it, people go, right, okay, 1, 2, 3, 4, 5. And you can see the difference between this one here and this one here. People tend to draw an extra line in because they're counting each line every time they've got a carbon atom. So 5 carbon atoms, people go 1, 2, 3, 4, 5, when actually they should be going 1 as soon as they put their pen down. 2, 3, 4, 5. So that's a little tip for drawing skeletal formula. If you're counting carbon atoms, as soon as you put your pen to paper, count that as carbon 1, 2, 3, 4, 5. And then just zigzag the rest of them. Okay? So that's the most simple basis of skeletal formula. And if you look back at that big massive compound that I showed you before, you'll see that there's lots of lines like that, so you'll be able to work out that these are just carbon atoms with hydrogens coming off them. Okay, so this one's quite different to other types of formula, so if you want to spend some time having a little look at that, that's absolutely fine. We'll move on and show you some other examples of skeletal formula. So these are also drawn skeletal. I'm going to show you what they look like as displayed formula. So if we look at the top one, and we look at the bonds that we've got one there, one there, one there, one there, and one there. So bonds between carbon atoms, we have got 1, 2, 3, 4, 5 bonds. In terms of the actual carbon atoms themselves, we have got 1 there, 2, 3, 4, 5, 6. And I'm just ignoring that OH at the top at the moment. So we've got 6 hydrogen atoms. So let's draw those in. 1, 2, 3, 4, 5. 2, 3, 4, 5, 6. There's my 6 carbon atoms and my 5 bonds drawn between them. So just to make it clear, that one, that one, that one, that one, and that one. There's my bonds. Okay. Now, coming off of one of the carbons, we have got another bond, but importantly, it doesn't go to a carbon. And we know it doesn't go to a carbon because we have got an atom on the end of it, a different atom. So as soon as a line goes to a different element, we know that there's no carbon there. So we have got atom number 1, atom number 2, atom number 3. Atom number 1, atom number 2, atom number 3. It's going to come off this carbon atom here. So draw it in. We've got an oxygen, which is attached to, I'm going to draw it full displayed, so I'm going to draw the bond in, a hydrogen. Now there's no other information on that diagram, so what do you think must go here, 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 there, 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 and there? What must go there? What's not drawn, and the bonds aren't drawn either, it's hydrogen atoms, always go around the outside. So draw them in, and that is turning something skeletal into something displayed. Okay, a little bit quicker through the others so that you're not spending too much time on this. Next one down, we have got 1 bond between carbons there, 1 bond between carbons there. So, carbon, there we go, drawing it out in the correct shape as well, just to make it a little bit easier to see. And we know that coming off the middle carbon, we have got a double bonded oxygen, so 2 bonds and an oxygen. We've got no other information, so if there's any gaps, they must be hydrogens. So if you have a little look around, is this oxygen making 2 bonds like I said it should? Yes, it is. Is this carbon making 4? 1, 2, 3, 4? Yes, it is. These 2 carbons, however, are not making 4 bonds, so we need to make sure that they do. 1 there, 1 there, 1 there, 1 there, 1 there, and 1 there. And what must go on the ends? Hydrogens. So there's the displayed formula for that one. Okay, moving over onto this one with the chlorine in it. This is a branched one, so it's a little bit different. Let's see, we've got 1 bond there, 1 bond there, and 1 there. And the other one doesn't go to a carbon because it goes to a chlorine. So we've clearly got a central carbon here going off to 3 other carbons there. So let's draw that in, central carbon. Oh, different colour, doesn't matter. We've got a carbon up there, we've got a carbon down there, we've got a carbon up there, and we know that that one goes down to a chlorine. So if it makes it easier drawing it in the same shape instead of drawing it in a nice straight line, that's absolutely fine. It's probably slightly more correct to draw it in this zigzaggy sort of shape. So that's all the information we've got. You need to have a little look. Is everything making the right number of bonds? This carbon needs 3 more, so draw in your hydrogens. This carbon is making 2, so it needs 2 more. Draw in your hydrogens. 1 down at the bottom needs 3 more. Draw them in. And this middle one, which is nice and easy to miss, because it's sneaking about in the middle, is making 3 bonds, so you're going to have to stick a 4th one in there with a hydrogen. And that's that turned into displayed formula. Okay, and finally we've got this weird looking thing down in the bottom corner. We have got 1, 2, 3, 4, 5 carbon atoms, and on the middle one we've got some more carbon atoms sticking up. So I'm just going to move some stuff around here. Okay, just make it a little bit easier to see. So we've got the 5 carbon atoms, 1, 2, 3, 4, 5. On the middle one we've got this bond here that goes to a carbon atom, and another one goes to another carbon atom. So middle one goes to a carbon atom, goes off to another carbon atom. Doesn't really matter about the shape. They're the carbons that we've got, they're the bonds that we've got. So we need to make sure that everything's making the right number of bonds and stick the hydrogens around the outside. Okay, so there you go. There's the carbon skeleton and all the hydrogens around the outside, and you can see why it's much easier to just draw this sort of weird shape much quicker. And that is skeletal formula. So I've got a few little rules just to help you out. So when you're looking at something skeletal, first of all, hydrogen, when bonded to carbon, does not have to be shown when the carbon isn't shown. So no hydrogens here, but there are hydrogens there, they're just not drawn in. Okay, so a line represents a carbon-carbon single bond. A double line represents a double bond. So this is a carbon-oxygen double bond, and you'll get carbon-carbon double bonds and other things like that. You get nitrogen double bonds and stuff. Okay, carbons do not have to be drawn in. So every time you get to a corner, you've got a carbon atom there. You don't have to draw in any lone pairs, but we'll deal with that in a little bit. If you've got a hydrogen that's bonded to something other than carbon, you should really draw it in. And then finally, you might see some weird bonds like this, so wedged bonds and dashed bonds. You do not need to worry about them until second year. It's just to show, if you could show it in 3D, that's how you'd show it in 3D. But they're the general rules, that's how you do skeletal formula, so we'll have a little play with it in class. Okay, and that is all of it. That is everything on formula. So that's molecular, displayed, structural, empirical, general, and skeletal formula. If there's anything you're not sure on, go back, have another little look at those parts of the video, but please make sure that you've got your tutorial notes ready for next lesson. And if you're ready, can you go back onto the blog and complete your post-tutorial quiz, please? It's 10 questions. It won't take you that long. Thank you.